Welcome again to the NPTEL course on storage systems. So, in the previous class we were looking at the global file system, the Google file system, GFS, and today we will look at some of the issues the design throws up and see what can be done about it. Okay. So, as I summarized last time, this is one of the largest file systems, probably still today I think it might be the largest. Okay. So, of course, they have moved to a slightly different version of this GFS. Sometimes that's called GFS2, sometimes called Colossus, I do not know what the various names are there. Okay. So, it is still living on in a slightly different form. And as we discussed before, it is not POSIX. And one critical thing about how without POSIX it is still okay is because they have ensured the applications are redesigned. And the way they do it is by using additional infrastructure on top of this. And the infrastructure, one important infrastructure piece on top of this GFS is something called the BigTable. Okay. We will look at that thing a bit. We will not go too much into detail because it is closer to application level ideas, but we will take a quick look at it to see what all it does and how it fits with the general GFS model. Before that, we will take a look at what are the problems with GFS. So, what is the issue about what are the issues with GFS? First of all, the design says high sustained bandwidth more important than low latency, and basically designed for batch oriented applications such as web crawling and indexing. So, this was a critical need in the early 2000 or late 1990s, but now what has happened is that Google has come up with other applications like Gmail or YouTube, etc. These are closer to real time, especially since Gmail is just a lot of user interaction. It is absolutely critical that there has to be some low latency also is an important issue. So, if you try to run Gmail or YouTube on top of GFS, you might get into problems. Okay. We will see what kind of problems there are there. Okay. First of all, because of these kind of newer applications, the developer base has moved from batch oriented frameworks like MapReduce to interactive applications. Okay. So, because you are no longer doing batch processing, it turns out the original design was not a disaster. What is the original design? Which had a single master and there was a single point of failure, SPOF. Okay. But it is unacceptable for latency sensitive applications such as video survey. Okay. In the beginning, in the early iterations of the GFS, there was no automatic failover scenario if master crashes in the very beginning. And it would be manually restarted. It could take as much as 1 hour because you have to look at the logs and replay the logs, etc. Okay. It will take quite a bit of time. Now there is supposedly, I don't know all the details, but this is what I read. There is supposed to be an automatic failover, but takes 10 minutes, but nowadays closer to 10 seconds. But even this 10 seconds is a problem because especially if you are talking about real time situations. So, as mentioned, there are shadow masters, but even those take some time to come up online. Okay. So, basically also what happens is that you have to write to 3 chunk servers. Their model of consistency is that model of completion of a write request is write to 3 chunk servers, and then if one of them happens to be slow, you slow down everybody because you wait for all 3 of them to respond before you proceed. Okay. So, this limits it to somewhat lower bandwidth situations, and basically you want to allocating a new chunk, etc., and then writing all those things essentially takes about multiple seconds. So, this is not a really good design for low latency. Okay. Other issue about this GFS is that because it was expected to be a batch processing application, they do a lot of queuing in the design. So, queuing is a way to smooth out variance in terms of arrival of jobs, etc. Okay. So queuing the design helps you to smoothen the flow of activity in the system, but the minute you start queuing, you have to first enter the queue and exit the queue. That itself will, there is some kind of delay that comes into picture, and basically the queuing delay essentially kills this low latency possibilities. Okay. So queuing is good for throughput, but generally bad for latency. Okay. So that's the reason why it turns out to be somewhat problematic, serious problem. Okay. Other issue that is an important issue also for GFS is that all the metadata in the master is in memory. That means it can only handle limited number of files, because if each file has about 100 bytes or so of data, that will essentially limit the number of files. Okay. So if you really want to go from 64 megabyte chunk to 1 megabyte chunk, okay, which is also required for other reasons, then this becomes a serious problem. Okay. So in the beginning the design was tens of terabytes or more, but now it is hundreds of petabytes. I am told that it is certainly crossed 100 petabyte. Okay. So with hundreds of petabytes, the amount of memory required for the master is crossing about 100 gigabytes plus. Okay. So this also is an issue. Okay. So if you have a single master, you don't have parallelism, because you cannot, if there is doing some scanning, recovery, etc., this single master turns out to be a problem also. Okay. Same thing when you have multiple map reduce clients, you will find that metadata serving also becomes a problem. Okay. So the early generation of GFS would do thousands of operations, but people want to do at least 1 or 2 orders of magnitude higher, and so having a single master is a problem. So having shadow masters like was designed earlier, as we discussed earlier, is of some help. Okay. But as we discussed before, the shadow masters are slightly behind with respect to updates of the master. Okay. So other issue is that nowadays there is an important requirement that if you have a new page you design and put it up on the web, you want people to be able to see it fairly quickly. Now the batch of operations does not allow for large scale incremental processing using distributed transaction notifications. Basically what happens is that you are limited to your batch processing, which can take about a day or so, and therefore the freshness of web result also becomes a problematic thing. So what you really need is, every time a new page comes online, you want to be able to somehow get some triggers that something new has come in, and using that trigger you want to be able to do some incremental work and put it up onto your this one, so that you have freshness of web results. But having this batch kind of model doesn't really help. Okay. So the batch is basically a killer for this kind of issues. So nowadays Google has has attempted to address this problem systematically. I am now told that if you put up a web page, it can be available to you within tens of seconds or hundreds of seconds, I don't know what the number is. They say that it can be made available as a result in the web search. Okay, precisely because they can do incremental processing. Essentially they have some kind of triggers which tell you that something has been added to it, and they immediately go and crawl it and index it immediately. Okay. So instead of multiple hours, it is now closer to, let's say, minutes or tens of minutes. Okay. Or sometimes they say even tens of seconds. Okay, which is a remarkable thing, which is not possible with batch processing. So we have to do something else. Other issue is, we already looked at the consistency issues. So I think we have gone through some of these aspects. We see that the clients keep on pushing right until it succeeds, right? Because you have to write to 3 places. Some of them can fail. You declare that if any one of them fails, you redo it, start from the beginning. Okay, keep on pushing it till it happens. But if you have client failures, then it causes indefinite state because there is no client to push the write. Okay. So again, similarly, there is record append interface. I think we discussed it for multiple writers. You want to write to a log concurrently, but what can happen is the primary itself can change as the write is going on because of failures. So primary selects offset to write, primary can change and new offset is taken. Okay. So therefore, record append does not offer any replay protection. Some piece of data multiple times in the file or data in a different order depending on how the new primary schedules the writes. Okay. Because the new primary decides how the various concurrent write operations are going on. Okay. So therefore, it is possible to have the data in multiple times in one chunk replica, but not in all on all. Okay. So if you read the data can be available in different ways at different times. So application has to work around these things, okay, which is a big issue. Same thing at record level, records in different orders depending on which chunks are read. Okay. So there are some of these issues. Originally it was thought that all these things can be handled somehow, but as people started writing applications, newer applications, this turned out to be big issues that had to be resolved somehow. Okay. And the system also had some other issues like snapshotting, which is a long running, which takes a long time, and so snapshot in general is a very difficult operation. As we noticed, you have to take back the leases, you have to wait for all the leases to come back, all kinds of things of that kind. It takes time. Okay. So generally a snapshot in any file system is difficult, and they had provided this functionality so that you can replace a replica, or whenever a chunk server goes down, we need to replace its files, basically have a snapshot so that you can repopulate it very quickly. Okay. But this turns out to be quite complex, and this has slowed down or created difficulties in other parts of the system. Okay. So what are the solutions to this kind of problems? Basically, you have multiple masters, and each master should be one master per data center. Okay. That's it. Okay. So you basically put multiple GFS masters on top of a pool of chunk servers, and you try to still avoid the complicated consistency issues that crop up because of this, and the way you do it is by partitioning data across different cells. Okay. You make sure that each cell actually has data which is not common with other cells, so that there is no issue of trying to do consistency across these cells. Okay. So the other issue is it possible to combine smaller objects and put into bigger chunks? Okay. But people have discovered that if you count the number of, there are some limits in the system. I think as you mentioned, number of files has an impact on the size of metadata that the master has to keep. So they tried both quotas on file counts and storage space itself, and typically their experience has been that you typically exhaust the file count quota first. That is, you still have enough space, but you don't have enough space to keep the metadata in the memory of the master. Okay. So they have come with a newer design point. Okay. 100 million files per master with hundreds of masters. Okay. These are the kind of new design things that are starting to, I think already is available, I suppose. I don't know the exact details. Some of the details are not available right now, exactly what they have done. I think the new system called Colossals probably has all these issues, has all these things taken care of. I picked up some of this material from various interviews given to various top designers of the Google file system. Okay. They discuss what the problems are, and but there's no paper as far as I know, okay, which talks about how they have solved the problems. Okay. Complete paper like the Google file system paper which came in SOSP, not that level of comprehensive detail and consistently discuss all the issues. That's not there yet. There are other issues. So these are the previous solutions were at the level of the systems level. Okay. You can also have application level workarounds. Okay. So Gmail uses what they call a multi-home model. So there are multiple essentially instances of your Gmail account. If one instance of a Gmail account not available, you just move to other one, and then you think about reconciling it later, okay, from availability point of view. Okay. So that's one. So an application essentially starts out assuming that it's a multi-home model, and then that's it. There is no systems. The systems infrastructure is not giving you a, let us say, a uniform view without having to worry about details. Okay. You have to take care of it yourself. Other issue is, for example, if you take BigTable as an application on top of the Google file system, it has got a transaction log, and so this application log, you might call it, okay, it turns out it's a big bottleneck because everything has to go through it. Okay. So what they have done is they have decided to duplicate the logs. There are 2 logs open at any point in time. You try to write to one, and because it is writing to 3 replicas and all those things, if it gets stuck, if it turns out to be slightly slower than you expected, okay, you just start moving to the other one. Okay. So things of that kind, but then things will go out of whack. So the logs will be slightly not exactly consistent with respect to each other. So you have to merge it, but a good thing is that you don't have to do it all the time. You do it only when you have to, some failure is taking place and you have to replay it. At that time you figure out what to do. Okay. So that's another way to work around the problem. Okay. So there are various issues of this kind that have cropped up, and various people have tried to do various different things. And the other approach is to use a completely newer type of infrastructure on top of GFS, which can be used to handle many of these issues, and that particular model is called the BigTable. Okay, it's for any application with lots of small data items, so that this BigTable allows you to create items, delete items in memory, and slowly it is pushed to disk in bigger chunks. So in a sense, this gives you ability to aggregate small piece of data and then clean that particular data at regular intervals, compact them, and then later when you want to make it persistent, you can push it out to the global file system, the big blocks. Okay, those kind of things can be done. Okay, so the idea is to do mostly stuff in memory, and then get the updates, and then clean the updates, that is whatever is needs to be garbage collected, whatever updates are no longer necessary, throw them out, keep on compacting them, reduce the amount of memory if possible. When finally it becomes bigger than what you can handle, then finally start thinking of pushing it out to disk. Okay, and finally GFS is now there in that picture. Okay, GFS will essentially storing it persistently. Okay. So let's just quickly look at BigTable. It's a structured storage system with many key value pairs and a schema. Okay, so this is used for web indexing, for things like Google, etc. Essentially, to put it in a slightly different way, it's a sparse, distributed, persistent, multi-dimensional sorted map. Okay, so essentially this is what is often called a key value store. Okay, you have a key, and then you give the key and look up the table. Okay, it is persistent. That means that once you collect enough data of these tables, you can make it persistent. Okay, and it finally is going to be stored by the Google file system. Okay, it's distributed basically because it is the various key value pairs will be stored across various nodes across the system. It is multidimensional because it can have, essentially this value can be many components. You can call it multiple columns. Okay, so you can take the key as representing the one row, and the value being multiple columns. Okay, so essentially it is like a table, just like a table with many rows and many columns, and this particular map is indexed by row key and a column key and a timestamp. Basically, the timestamping is used so that you can have multiple versions of the same piece of information, and you always keep the most recent information accessible the earliest. Okay. So, the later ones you have to take some trouble to traverse the list. Okay. And to make it as general as possible, each value in map an uninterpreted array of bytes. Okay. Just like, for example, like the way Unix also treats files, it's uninterpreted set of bytes, same thing here, anything you can put in. Okay. There's no structure there. The only structure we have is that it is a sorted map and it is sparse distributed multidimensional persistent structure. Okay. So, for example, so what BigTable essentially you can summarize as follows. It's a row which is a string, column which is multiples, it's a string, but it can also be seen as multiple strings, so that you have multi-dimensional aspect to it. Time is basically a set of let's say time instance at which these particular data were created or modified, and it's int 64. So, if you want to it's your business to make sure that this is different from every other time instant. So, okay, you have to ensure that this real, you can use real time, but if real time happens to be at the same time, for example, then you have to find some way of achieving it. Okay. So, an example of the way BigTable can be used is you can store, for example, if you are crawling the system, crawling the web, the URLs could be row keys, various metadata categories of web pages, column names. For example, you may want to categorize the web pages as depending on which language it is, for example, whether it's English or any other language, okay, Hindi or whatever, right? So, that is basically the column names, and then you can also have contents of web pages, that also is another column, okay, and then the timestamps, okay. So, and all the data is usually kept in lexicographic order, okay, by row key. Every read or write of data under a single row key is atomic, okay, in spite of the number of columns, etc. Okay. So, one thing that we guarantee is that reading, writing of data under a single atomic row is atomic. Okay. They do not say anything about what happens across rows, but a single row is what they guarantee, okay. And you have to figure out, your application has to figure out how to get their job done with this particular guarantee, okay. The first important thing to know is that this BigTable is essentially a storage design, it is not a database design, okay. It is not a relational data model, okay. Basically, the understanding is that databases have problems of scalability, serious problems of scalability. They cannot cope up to the kinds of demands that current web, etc. places. So, the idea is not to go with a relational data model, and it provides clients with a simple data model that supports dynamic control over data layout and format, okay. So, and the way that is done is by what we just discussed already. We have a set of rows, set of columns, and we just have a key value pair kind of model, okay. That is basically a simple data model, okay. And it allows clients to reason about the locality properties of storage represented in the underlying storage, okay. So, essentially they can, the clients can dynamically control whether to serve data out of memory or disk, okay. All these things are possible. Clients can control locality of the data through careful choice in the schemas, okay. They provide enough control so that the clients can figure out the issues with respect to locality, okay. So, the data can be, data is indexed using row and column names that can be arbitrary strings, okay. Again, as we said before, it treats data as uninterpreted strings, but clients can serialize it into various forms of structured and semi-structured data onto these strings, okay. basically in some sense you decide how you serialize the data as a string. Okay, it's up to you. Okay, but they just, so I think it's similar again to the way the Unix file system does it. Okay, anything in a file, it's your business how to make it as a set of series of bytes, and it's under your control. Okay? So it's essentially some kind of Unix kind of model. Row range for a table dynamically partitioned. Okay, so you can take, as I mentioned, all the data is lexicographically ordered, and so basically you can take a set of rows and then you can dynamically call it one tablet. Okay, and this tablet is unit of distribution and load balancing. Okay, multiple rows become a tablet, and that's basically unit of distribution and load balancing. Because it is that way, reads of short row ranges efficient. Basically, they all are there in a single machine. So it requires, if it is a fairly large tablet, it might at the most span a few machines. So you just have to talk to a few machines. Okay. Clients can select the row keys for good locality of data accesses. Again, client is given complete control about how they can order things. Okay. For example, if you are storing web pages, the way you can do it is to get locality is to reverse the URL. If you reverse the URL, the last component is basically the site name, right? And therefore, you can use that as basically pages in the same domain grouped together. Okay. So, for example, if your website is x.y.z, okay, you make the name as z.y.x, and z dot basically is the, you might call the major let's say organizational boundary, and therefore all those pages will be connected probably similar in the same place. Okay. So pages in the same domain grouped together, okay, by reversing host name components in the URLs. So again, this is all up to you, because the system, nobody is telling you that this is the way it has to be done. The clients can design all this. So another thing that they have is what they call column families. Column keys grouped into sets, and basically this is the family and the qualifier. For example, family could be language, for example. Okay. And good thing about this is that all data stored in a column family typically same type, and probably they might even have same type of data also. So it turns out because of this, you can compress data in the same column. If you compress them in the same column family together, you get much better completion ratios. For example, in one column you may have some names. It's very likely that there's a lot of commonality in the names. So if you compress a group of columns in a column family, there's going to be a lot of possibilities for compression. When across rows, usually the rows will have columns from disparate types of objects, and therefore they will not probably as well at all. Okay. So that's also one reason. Okay. So the number of distinct column families is small, but a table may have unbounded number of columns. Okay. Number of columns may be quite large, but column families, that will be reasonably small. Again, BigTable, it uses our infrastructure as we already looked at, as we already seen. It uses definitely GFS. It is also something also called Chubby. Okay. First thing to notice is that GFS provides only two basic data structures, logs and what they call SS tables. Okay. And they also have something called protocol buffers. We are not really gone into details, but basically the idea is that if there is some understanding about how to specify how data is structured, then there is going to be less effort at transforming one type of data type into some other type of data as required. Oftentimes this takes a lot of computation, memory, and energy. Okay, and for example, I have a data format. It could be one form in Java, it could be some other form in some other language, and every time you move this kind of boundaries, application boundaries or system boundaries, you may have to convert it from one type of format to another type of format. And once you start doing it systematically, the inefficiencies start mounting seriously, and you will find that there is going to be a lot of performance loss. So one thing they have tried doing also is have at application level some idea about how you structure the data, and the name they are given is something called protocol buffers. Essentially, it actually should be called a data description language. Okay? It tells you how the data should be described, possibly even things like how it is different systems will have different ways of padding other things. In spite of all these things, they should be accessed in a uniformly same way and avoid as much as possible the conversions from one format to another format. Okay. So basically what happens is that you are transferring data from one system to another system using this kind of protocol buffers, and these things are finally ending up in logs or what is called SS tables, and these things are persistent. But while these things are being they're persistent, you need to keep them in memory as they're being constructed. Okay. So that's where the BigTable and GFS come to picture. The SS tables are immutable. That is, once you have figured out that you want to store that amount of logs that have been created because of changes in the system, once they cross a certain boundary and it can be easily returned to one chunk, for example, then they become immutable. Okay. Whereas BigTable is working on in memory, and it will give you the storage that can be changed, because you can add a row, delete a row, you can remove a column, add all kinds of things you can do, right. So those all the things operations will be done in memory, and once all the changes, logs, etc. correspond to these operations, you want to make them persist, then they finally go and reside in the GFS kind of GFS. Okay. So again, if you think about the division of labor, you see that GFS provides this something called SS tables. These are immutable, means they're persistent, and either you read them completely into memory, change it, and then write it back. Essentially, you might say it's equivalent to doing read, modify, write operations, and that's why they're calling it immutable. You can't really change it. There's no API by which you can go and say into a chunk, change this part. Okay, you have to get into memory and do something with it, then write it back fully. Okay. Well, BigTable provides mutable key value storage. Okay. So essentially what's happening is that any incoming data is stored into transaction log files, and then as you proceed in the system, some of those changes might, they might have to be thrown out. Okay. You can essentially say that some of the changes are, let's say, obsolete, you can throw them out. So basically you can compact them again. Okay. And then you keep on doing it. Finally, once you find that you're running out of memory, etc., you want to store it persistently, then you push it out to GFS. Okay. It's similar to a log structured file system. In a log structured file system, what you do is there is no home locations like in a general kind of file system. Basically all the operations on the file system happen in memory as a log. Okay. And as the log keeps increasing, all the changes are actually stored in memory called segments, and once the segments become full, you want to reuse that memory for newer types of changes. Then what you do is you clean them, you clean those segments so that all the obsolete changes that no longer needs to be kept around. For example, you modified a file 3 times, so the intermediate changes need not be stored. Okay, they can be thrown out. You just have to keep the last one. So you can clean them and then write back to disk. And the idea there, of course, is that once you accumulate a megabyte or a few megabyte kind of changes, logs, you can write it in efficiently. You can write those long, bigger chunks of writes fairly efficiently. That's what log structured file system does. So here also we do the same thing. Okay. So the BigTable provides the mutable key value storage. You accumulate the changes in the form of logs, and then the logs, when they become, you clean them now and then so that you can memory more effectively. But once you have come to a stage where, in spite of cleaning etc., it is growing beyond the size that you want to keep in memory, then you start pushing it out to disk, and the way you do it is to send it out as chunks to GFS. Okay, that's how GFS and BigTable work together. Okay. Another thing that the system uses is something called Chubby, which is basically a highly available and persistent distributed log service, okay, and uses Paxos. So it's got 5 active replicas with an elected master to actively serve requests. Okay. Again, this is a log service, so it is used in whenever you want to have mutual exclusion, okay, across multiple. For example, you want to make sure there's only a single master, then you use a log, the Chubby. Okay. So what are the things that BigTable provides? It creates, you can create and delete tables and column families. You can change some metadata, for example, or correspond with some of these objects like tables and column families. You can, the client applications can write or delete values in BigTable, look up values from individual rows, or iterate over a subset of the data in a table. You can do all these things. Okay. And various ways you use the system is that single row transactions to perform atomic read modify write sequence, okay, and the single row key is possible. Okay. Basically, get the whole row, change whatever you want to change and put it back, okay, because you have single row transactions which are atomic with respect to both read and write. But you don't have any general transactions across row keys, multiple row keys, not possible. Okay. They also have some additional features. Basically, they are able to do read-only memory maps from what I can understand. Therefore, you can support execution of client-supplied scripts in address space of servers. Okay. So, allows data transformation, filtering based on arbitrary expressions and summarization by operators, but no write back into BigTable. Okay. So, I think from what I can gather from this is that there is some kind of memory map is available on the intermediate memory structures, and they can be used as a way to do everything in memory, but you can't write to BigTable. You still have to go through the sequence I mentioned earlier, that is basically this sequence, go through SST tables and then make it persistent. Okay. So, that's the only way to write it back to BigTable, is to GFS. Okay. So, so the idea again is to make sure that you can efficiently execute various types of operations like data transformations or filtering in memory, and I think from what I gather, it is going to be, it's using memory map to mmap to do all these things. Okay. Other thing that they support is they have some various facilities so that map reduced jobs can be supported well. Okay. Basically, this BigTable can both be an input source as well as output target for map reduced jobs. Okay. So, what are the various components of the BigTable? They have 3 main components: a library that is linked into every client. Again, they have a single master server and many tablet servers. Okay. So, tablet servers dynamically added or removed from a cluster to accommodate changes in workloads. So, basically, what is a tablet? We mentioned that a tablet is a bunch of rows. Okay. So you can have various machines, various nodes will have various tablets, and therefore that's the way you can get the scaling that you as to increase the performance. Okay. So you can tablet servers can be dynamically added or removed from a cluster to accommodate changes in workloads. Okay. So this is how the dynamicity in the system is provided, and the master is responsible for assigning tablets to tablet servers. So tablets are basically a bunch of rows, and tablet servers are nodes, so somebody has to do assignment, and that's what the master is doing. Again, the reason why this gone for a single master is for the same reasons why GFS has gone for a single master, for the same reasons. So basically that the single master has complete view about what is going on. So again, detecting addition and deletion of tablet servers. Basically, if a tablet server dies or comes online, you can do those things. Okay. Balancing tablet server load. So again, you can move tablets around or resize the tablets depending on the load. Again, even garbage collection of files in GFS is initiated by the BigTable master. Okay. So if there is some extreme, if there is serious shortage of spaces, etc., some of them can be made to start doing the garbage collection immediately. Okay. So then other things that the master does is also handles schema changes such as table and column family creations. Okay. If you have to add a column family, okay, then you have to essentially do it for all the rows, right? So you have to do something, you have to do systematically go iterate over all the rows and do something with it. So all those kind of things are handled through the master. Okay. So again, as I mentioned, the persistent state of a tablet is stored in GFS through memtable. Basically, memtable is the in-memory structure which has all the changes, I think like we discussed here before, right? So all the changes, for example, they go into the memtable, and this bit, and then these memtables are compacted, and these SS tables are created, and these SS tables get compacted together over time, and they finally get into GFS. Okay. So that's what the persistent state of a tablet is stored in GFS through operations on the memory table. Okay. So okay, I think I'm at the end of my discussion today. I thought I will take more time, but this is where I am. Okay. So I think I'll continue next time with further discussions on BigTable.